The diode is a nonlinear circuit element and a two-terminal semiconductor device formed by two doped regions of silicon separated by a p-n junction. An analytical expression for the relationship between the voltage V and the current I for the diode can be written as follows. The parameter Vt is equal to Kt over Q is called the thermal voltage, and the constant Is is the saturation current. For silicon, Is is typically 10 power minus 12 amps. Vt, the thermal voltage, is approximately 25 millivolts at room temperature. N will be assumed as 1 unless specified otherwise. Typical measured Vi characteristics for silicon diode are on your screen. The current appears to be 0 until the diode voltage is almost 0.5 volts, at which point the characteristic starts to rise. This apparent knee is entirely due to the mathematical behavior of exponentials rather than some physically related threshold in the device. Nonetheless, on the scale of milliamperes, silicon diodes appear to have a threshold voltage of 0.7 volts. This threshold has important consequences for semiconductor circuit design, some detrimental but others of great value. This characteristic of the diode is when the diode is forward biased. This is a mode of operation. For an ideal diode, the IV characteristic looks like this on the bottom right. Let us look at the currents inside the device under open circuit. That is, we remove the external voltage. There is a diffusion current ID, which is caused by the electrons diffusing across the junction into the P region and holes diffusing into the N region, shown here with blue arrows. In the P side, the thermally generated electrons are swept into the N side by the electric field, shown by green arrows here. Similarly, some of the thermally generated holes in the N region are swept into the P side by the electric field. This causes a current in this direction called the drift current Is. This current is temperature dependent but independent of the depletion layer voltage. Under open circuit, ID equals Is.